In this lesson, we're going to revisit one-sided limits. And last time we looked at the Heaviside function. Let's review that quickly from the last video. I'm going to draw in, it's not very visible, so I'm going to draw in the part of the function we can't see very well, and it is defined up here at 1. We looked at taking the one-sided limits for this function. We said the limit of h of t as t approaches 0 from the left equals 0. And we said the limit of h of t as t approaches 0 from the right equals 1. And you can verify that with the graph. As x approaches 0 from the right, you can see that the y values are approaching 1. Our conclusion was the limit of h of t as t approaches 0 then does not exist, because in order for a limit to exist, the one-sided limits have to equal each other. So let's look at the definition of a one-sided limit with the Heaviside function in mind. We have the limit of f of x as x approaches a from the left equals L. We say that the left-hand limit of f of x as x approaches a is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a and x less than a. If we looked at this graphically, say we have some function here, that's our y equals f of x, and we are looking at this limit at x equals a, we're saying we can get as close as we would like to this limit L by taking values of x closer and closer and closer to a, and we can get as close as we want to this value L by letting values of x get closer and closer and closer to a. Likewise, for the right-hand limit, we have this definition. So I'll let you read through that, or you can pause the video and read through that to make sure you have a good understanding of this definition. Let's look at a one-sided limit graphically. Here we have the graph of x cubed minus x plus 2. We're trying to find the limit of this function as x approaches 1.3 from the right. So let's do some analysis. Here is about 1.3. So as we approach this value from the right, what's happening with the y values? We look at the corresponding y values and it's approaching, it appears to be about 2.5. Here's another limit, a one-sided limit. The limit of our function as x approaches negative 1.5 from the left. So let's identify negative 1.5 here. We're letting values of x approach negative 1.5 from the left. And let's look at where are the y values heading towards this value here, 0. So for this one-sided limit, we would say 0. Another definition. The limit of f of x as x approaches a equals L if and only if, then we have these one-sided limits. So these one-sided limits, the left-hand limit must equal the right-hand limit. Now let's explain what's going on here a little bit. Remember a conditional statement. A conditional statement is an if-then statement. This is called a conditional statement. You have if, and then you make some hypothesis. Then you make a conclusion. That's an if-then statement. This one says if and only if, which means it's a biconditional statement. That means if I switched the conclusion and the hypothesis, it is still true. For instance, if I said, if it is raining outside, then the grass is wet. True statement. What if I switched the hypothesis and the conclusion? If the grass is wet, then it is raining outside. That's not necessarily true. The sprinklers could be on. So that would not be a biconditional statement. This is a biconditional statement, so I could switch the hypothesis and the conclusion and it would still be true. So let's find the following limits if they exist. So part A says the limit of g of x as x approaches 2 from the left. So I'm going to let, this is our function g of x as you see on the screen. I'm going to let my values of x approach 2 from the left. And I'm going to analyze the corresponding y values. The y values are approaching, it appears, 3. And unfortunately, I didn't leave enough room, so I'm just going to squeeze it in up here. This equals 3. Part B, the limit of g of x as x approaches 2 from the right. Again, this is a one-sided limit. So I'm only concerned with what's happening from the right of 2. So I look at the values of x approaching 2 from the right, analyze what's happening with the y values, and it looks like they're approaching 1. So for part B, I would say this limit equals 1. Now for part C, since I'm looking for the limit of g of x as x approaches 2, I found that the one-sided limits do not equal each other. Therefore, this limit does not exist because the one-sided limits do not equal each other. Part D, the limit of g of x as x approaches 5 from the left. So as values of x approach 5 from the left, let's analyze what's going on here. Now, this graph is trying to trick us a little bit because you can see when x equals 5, the function is defined right here. However, we're not concerned where the function exists at that point. We're trying to find what are the y values approaching The y values are approaching, and that looks to be about 2.75. We don't say the y values are approaching 2, even though it's defined right there. The y values are approaching 2.75. We estimated there, so I'll just say 2.75. Part E says the limit of g of x as x approaches 5 from the right. And again, we're not concerned with where the function is defined. We want to know what are the y values approaching. And again, it looks like it's approaching 2.75. So now part F, we can make the conclusion that this limit does exist and it equals 2.75 because the one-sided limits equal each other and they equal 2.75. Therefore, the limit of g of x as x approaches 5 equals 2.75. Now we're moving to a new concept called infinite limits. Let's look at an example to help explain what is an infinite limit. Let's look at the function 1 divided by x squared. So we're going to try to evaluate the limit of 1 over x squared as x approaches 0. In order to determine if this limit exists, let's look at the one-sided limits. So first of all, let's look at the limit of 1 over x squared as x approaches 0 from the right. Now, if we look at values of x approaching 0 from the right, what's happening with the corresponding y values? Well, we can see they're moving up the graph like this, and it appears they're heading off to infinity. Now, I am going to write that this equals infinity. That does not mean the limit exists. This limit actually does not exist since it's not approaching some number. Infinity is not a number. But we're going to write infinity for informational purposes. That tells us something about the graph. But still, this limit does not exist. So if I put does not exist, that is still correct. But I am going to write infinity for the informational limit. Let's look at the other one-sided limit of 1 divided by x squared as x approaches 0 from the left. If we let values of x get closer and closer to 0 from the left, we see the y values are also going off to infinity. So I am going to write the informational limit infinity. If we wrote this limit here does not exist, that would be correct. But typically we will write an informational limit if we can. So I am going to say, yes, this as an informational limit is going off to infinity. So I can say the limit of 1 divided by x squared as x goes to 0 equals infinity. That's the informational limit. If this function happened to look like this instead, and I analyzed the one-sided limits, I could not write even an informational limit for this graph if I had a graph that looked like this. I would have a one-sided limit as x approaches 0 from the right equals positive infinity, but the limit from the one-sided limit from the left is negative infinity. So I could not write anything other than the limit of f of x as x approaches 0 does not exist. I couldn't even write an informational limit because even in order to write an informational limit, they both have to be either going to positive infinity or both going to negative infinity. Okay, another definition. Let f be a function defined on both sides of a itself, then the limit of f of x as x approaches a equals infinity. Now this is the definition for an infinite limit. Means that the values of f of x can be made arbitrarily large by taking x sufficiently close to a but not equal to a. So I would encourage you to look at this graphically, draw a graph, and make sure you can make this make sense in your own mind. This is the definition also for an infinite limit, but this one going to negative infinity. And you could pause the video if you'd like to write this down. Now we can use limits to identify vertical asymptotes. Notice this definition says the line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. So only one of these statements must be true. If I can show that the limit of a function as x approaches some number from the left is going to negative infinity, I have just shown there's a vertical asymptote at x equals a. So you don't have to show more than one of these to indicate there's a vertical asymptote at a. Here's another example. Find the limit of 2 divided by x minus 3 as x approaches 3 from the right. So let's take a look at that one first. So let's identify 3 on our graph first of all. So we're going to take values of x that are approaching 3 from the right side of 3. Now, if we looked at the corresponding y values, it appears that those are heading off to positive infinity. Now, if I just directly substituted 3 into that function, I would have 2 over 3 minus 3, which gives me 2 over 0. So that does indicate that we do have an asymptote at 3. The limit of 2 divided by x minus 3 as x approaches 3 from the left. So I'm going to let values, whoops, the marker took off on me there, approaches 3 from the left. The y values are going off to negative infinity. So this one we said was going off, this is the informational limit, to infinity. This one, negative infinity. So what could we say about the limit of 2 all over x minus 3 as x approaches 3? The only thing we could say is this does not exist. We can't even write an informational limit for this one. Find the vertical asymptote of f of x equals the tangent of x. Well, here's a hint. Tangent of x equals sine x over cosine of x. So this function would be undefined when cosine of x equals 0. And we know that the cosine of x equals 0 when x equals pi over 2 and 3 pi over 2 between 0 and 2 pi. Now for this graph, I'm going to estimate pi over 2 is about 1.57. So here is 1. So this would be about 1.57. So we would have an asymptote right in here, it appears. And then same thing at 3 pi by 2. We're going to have an asymptote right in here. So it says find the vertical asymptotes of f of x equals tangent of x. We know that if we look at the limit of the tangent of x as x approaches pi over 2, from we could either choose the right or the left. Let's choose from the left. As values of x approach pi by 2 from the left, we see that the graph is heading off to positive infinity. So there we've just shown there's a vertical asymptote at pi by 2. We could do the exact same thing for 3 pi by 2. Now we could do the same thing for every rotation around the unit circle. So if we added 2 pi to pi by 2 and added 2 pi to 3 pi by 2, we would get, again, a vertical asymptote. So if we wanted to represent all of those values, we could say at pi by 2 plus, now to get to 3 pi by 2, we'd have to add another pi by 2. We'd have to add another pi. And then if we're at 3 pi by 2, we could add another pi to get to that value again. And so we would be adding values of pi. So if we let n be an integer, so if n is 0, our first value would be pi by 2. If n is 1, we'd have pi over 2 plus pi, which is 3 pi over 2. If n is 2, then we would get the next rotation and so on. And we could let values of n be negative also. So we could pick up these asymptotes over here also. So our vertical asymptotes would occur at x equals pi over 2 plus pi n. Another example, the limit of ln of x as x approaches 0 from the right. So if we're approaching 0 from the right, here's x equals 0, and we're approaching 0 from the right. Let's analyze what's going on with the y values. We can see the y values are going down like this. And we know with the ln function, ln of x, we have a vertical asymptote at x equals 0. So our conclusion would be the limit of ln of x as x approaches 0 from the right is negative infinity. That is our informational limit.